Throwing is a system that's been more and more adopted by humans. It allows us to be efficient and increase our area of work. This has been used in very good ways, such as construction, but also in harmful ways that can be seen when we throw things that are uncontrolled. In our project, we wanted to try and take this into robotics. Currently, throwing that's been done by TossingBot is able to take an object and throw it further out of its working area into a desired goal. We want to expand on this, and rather than just throw it into a box, throw it to another robot. We wanted to first facilitate this through juggling. That's why we want to introduce JuggleBot. We've seen work done by REI Institute on other robots to also improve the working space of robots. This can be done through hitting balls and also through throwing and catching. This has been focused on impotence control to be safe with humans. However, other research that's been done focuses more on different robot objectives. Firstly, we see a change in a robot to a different sort of clipper that focuses more as a funnel rather than a claw that closes and opens. We wanted to build off this and implement a claw to claw, throw, and catch. Other things that have been done focus on different approaches, such as quad rotors, and also the physics behind juggling, and how us as humans use contact forces to our advantage.
For our approach, we want to use a keyframe approach. This allows us to first take our robot, the ball, and the target position, and take out the position of the ball and calculate our joint angles through inverse kinematics. We then apply the joint angles to our robot, move to the area, and pick up the ball. From here, we then use motion planning through creating a trajectory from kinematic solutions. From this, we are then able to calculate our inverse kinematics for each joint, take each joint's positions over the trajectory, and interpolate given a time constant. We then get a full trajectory, which we can implement keyframes for the claw to close and open at different points. This allows us to create a throwing trajectory as the claw gradually opens between the 2 points. We then use this to implement a keyframe solution. Here's an example of our robot throwing and catching. Our first conflict we ran into was how to get the time of the claw to pick up the ball properly. For this, we use inspiration from previous year's works. We saw that possibly trying a horizontal throwing approach rather than a vertical throwing approach allows us to easily grab and throw balls. We then implemented this in 2 different ways. We tried this side gripping, but we found that it's not easy to throw from the second arm. From here, we created a simple throw and catch. But when we tried implementing it with 2 robots to throw and then immediately catch after, we found that they errored out, even with a PID controller. And this was a result of us losing the key torque generation joints that the other projects didn't need. For this, we decided that we needed to make use of the wrist torque and the main angle torque. For this, we set up our robots one in front of another so we could make use of these joints. Here we see our solution where we use keyframes and inverse kinematics to solve continuously. However, we see that at each cycle, the robots are actually changing, and it's not a completely repeating cycle. And this is a result of key observations on where we're gripping. When we first pick up, we're gripping at the very end of the claw. However, as we begin to continue to throw, we see that our gripping area changes. This leads to very erratic throws, and even with inverse kinematic solutions, we're not able to get a repeating throw. To show that our robots could actually throw and we weren't having the same problems as side to side, we set up a 2-ball juggling and showed that our setup could actually work. Knowing that our setup works and we could get the throw and catch, it was now time for us to find a more innovative solution to be able to fix our different catching positions and slippage.
To address these challenges, we designed a controller system that can better react to the ball's motion. In our current keyframe approach, we can catch the ball given that we know its trajectory. However, if we don't know the exact trajectory or there's some environmental noise, the arm misses. So, we designed a reactive system that uses the ball's position and velocity to predict where to intercept a catch, even if the ball's trajectory deviates. Here's a demo. Our first arm picks up and throws the ball with a given velocity. Our second arm predicts the motion of the ball as it moves in the air and catches, achieving 90% accuracy under small perturbations of the ball's velocity and position. We latch onto the ball based on the distance between the gripper and ball and rotate upwards for a better grip. Extensions to this approach would include adding depth cameras so we can perceive the position and velocity of the ball, and also implementing antipodal sampling for more reactive gripping. As for real-world applications, currently assembly lines are in 2 dimensions, only able to interact with each other side by side. However, we propose extending to 3 dimensions, able to throw objects above and below.